Hello, everyone, and welcome to today's presentation. My name is Janine Donnelly. I am the Manager of Webinars for IBM Systems Magazine, and I will be the moderator for today's event. Today's webinar, entitled Reduce MLC Without Capping, Automating Resource Groups, is sponsored by ThruPut Manager. Our featured speakers today are John Baker and Peter Enrico. John Baker is a ZOS performance specialist with over 20 years of experience as a user and consultant. He has designed, implemented, and maintained many critical projects such as WLM goal mode and GDPS data mirroring, and has assisted many of the world's largest data centers with their ZOS performance challenges. John has held subject area chair positions with CMG for several years and is a popular speaker at CMG, Share, and IBM conferences. Peter Enrico is the owner of Enterprise Performance Strategies, Inc., and the lead designer of Pivotor, a modern, leading-edge SMM data mining and ZOS performance reporting tool. Not only is Peter a ZOS performance expert, but he's also an effective lecturer and seminar instructor. Peter teaches performance workshops on a variety of topics, including general ZOS performance, Workload Manager, WebSphere application, parallel sysplex, and much more. Today, John and Peter will reveal how source groups really work under the covers and how groundbreaking automation delivers new value to this old function. With our introductions complete, John, I will turn the presentation over to you.
Thanks, Jean, and thank you, everyone, for attending across time zones, it seems. I want to say first, I'm really happy just to be partnering with my buddy Peter for this session. He's forgotten more about WLM than most of us will ever know. What some of you don't know is actually he plays a pretty mean game of Donkey Kong as well. That's another story. We've got a simple agenda. First, Peter's going to introduce WLM resource groups and talk about how they work internally. We'll discuss how resource groups are typically used, and we'll look at some actual customer data processed with Peter's Pivotor analysis tool. Then I'm going to talk about what more can be done. We've developed new automation within ThruPut Manager to utilize resource groups in a different way than I think they were originally designed. We're really interested in what you think as well, so we reserve lots of time at the end for questions. And now, without further ado, I am going to turn the mic over to Peter. You got the ball, buddy.
I'm here. Okay, thank you. Hi, everybody, and thank you for allowing me to present today. I want to thank the ThruPut Manager people, and I want to thank all of you for attending. And today, what I want to talk to you about is WLM resource groups, because I know that ThruPut Manager uses them. And so what we wanted to do was to kind of give you some additional insight into what's happening behind the scenes as it relates to resource groups. So the screen you're looking at now, or the slide you're looking at now, is just a general resource group overview. And as it says here, the objective of resource groups is to satisfy a service class period's goals within a bounds of a defined amount of capacity. So what we're doing here with resource groups is we limit or ensure the amount of capacity being needed or given to the resource group by, for the work that's running in the service classes in the resource group. And at the same time, we're going to try to meet the goals for those resource groups. So what we have here is what we call resource group minimums. And the reason we have minimums is to help ensure CPU capacity across the sysplex. In general, if a service class period is not meeting its goals and it's below its minimum, WLM is going to try to move the controls around in order to ensure that that work gets the CPU that it needs in order to meet the goals. And we have the concept of a maximum, which is used to limit the amount of CPU capacity across a system or across a sysplex. So given a maximum, what WLM is going to do is say this resource group work, this work running in the service class that's in the resource group, we're going to limit the amount of CPU it consumes down to the maximum. So what I'm showing here on the left-hand side of the screen is some amount of capacity, and I'm trying to show that there's 3 different service class periods in the group, and we have a certain amount of minimum and a certain amount of maximum. And in this case, the minimum and maximum is in regards of service units per second. So the general construct is we have this thing called the resource group, so we assign a minimum and maximum value to the resource group. The resource group is then assigned to one or more service classes, and then as WLM is running, as the work is running, CPU service is consumed and evaluated, and then the maximum is either going to be imposed, which we're going to talk more about in a moment, or the minimum is going to be enabled. Now, down at the bottom there, I do want to mention that maximums and minimums can be specified in a number of different ways. One way is in terms of unweighted CPU service units per second, which is the example on this slide. I want to limit the amount of CPU being consumed by the work to, let's say, 5,000 service units per second, or CPU service units per second. You can also have minimums and maximums in terms of percentage of an LPAR. I want this work to be limited to 25% of an LPAR. And the reason that's very valuable is as you increase the size of an LPAR, as you go in terms of the number of, let's say, the CPUs in the LPAR, the percentage may not change because you still want to say 25% of an LPAR, no matter what that size is. And then finally, we have CPUs of capacity where you really want to limit it to a certain amount of CPUs of capacity. So the case there is I want to limit the amount of work to be, let's say, not use more than one CPU's worth of capacity, not use more than 1.5 CPUs of capacity. That's the general overview of resource groups. But as it relates to ThruPut Manager, what ThruPut Manager is doing is they use what we call resource group maximums. So what I want to do now is just really kind of concentrate more on maximums, and we can save minimums for a different discussion. So what we do is we use the concept of capping, or resource group maximums, to limit the amount of CPU across the system as sysplex for all the service class periods within the group. So you can have one or more service classes in the group, and you can limit the amount of CPU being given to that group. Now, here what it says is WLM will still try to meet the goals for the service class period within the group, but the maximum takes precedence over the goal. So no matter what goal you give to the work running in a resource group, WLM is still going to try to meet that goal, but it could be that because of the maximum or how severe the maximum is, that the goal might be missed. And the attitude of Workload Manager is, hey, you gave it a maximum, and that's going to take precedence over the goal because the maximum is considered a contractual limit. So what we're doing here with the diagram is I'm trying to show that, let's say the blue area that we're looking at has a certain amount of demand. Let's say it's a batch job or a group of batch work. And that batch work has demand for 21% of an entire LPAR. The 5 boxes on the right-hand side each represent different resource groups. And in this case, I'm trying to show the whole area is 100% of an LPAR. So what the black bar is across each one is representing a cap value. The group number 5 listed towards the left is going to have service class period E in it, and it's limiting it to 20% of an LPAR, and then so on. So group 4 is I'm limiting to 15% or 10% of an LPAR as group 3 represents. Group 2 represents 5% of an LPAR. Group 1 represents 1% of an LPAR. So here you have some work that demands 21% of an LPAR, and as that work, or if that work is moved to each one of these groups, the work is going to be capped, not down to the 21%, of course. It's going to be capped to whatever percentage of the group represents. So let's say, for example, we take group 3, which is 10%. The work wants to use 21% of an LPAR, but it's going to be limited to 10% of an LPAR. So the area above that is work or CPU that is actually saved, MSUs that are actually not consumed for that work that would have used it otherwise. This particular slide represents how resource groups actually work. And the way a resource group actually works is through something called sleep slicing. And sleep slicing is used to enforce resource group maximums. So what happens is each period in a resource group is given what we call a sleep slice pattern. And the pattern is listed here towards the center of the screen where at least I can see white and red squares. Now what happens is every SRM second, and all you need to know about an SRM second is that it's a very small amount of time that represents something less than a wall clock second, is divided up into 64 slices. Now, as of ZOS 2.1, because we have faster and faster CPUs nowadays, this has changed to 256 slices. But regardless if it's 64 slices or 256 slices, it's really the same concept. What's happening here is that depending upon a number of different factors, that a sleep slice pattern will be developed. And I'll explain more about that on the next slide. But you can see here that the sleep slice pattern has a series of slices that are represented in red, which we're going to call sleep slices, and a series that are represented in white, which are going to be called the wake slice. And the way it works is we know that we have some number of logical processors assigned to a particular ZOS partition, and work can be assigned to those processors. So on the right hand side, we have something which we call the dispatcher queue. This is the work waiting to use a CPU. And when I say work, I'm talking about dispatchable units of TCBs and SRBs, which really represent our programs that want to run. So the work on the dispatcher queue is ordered in terms of CPU dispatching priority, and the work going on the queue as it gets to the front of the queue gets to be dispatched. Before a unit of work is actually dispatched to a processor, the current slice is looked at. And if the slice is a wake slice, it gets dispatched. If it's a sleep slice, the work does not get dispatched and instead gets placed to the end of the dispatching priority of that particular group of work. So I'm trying to show here that it gets placed to the end of the queue for that dispatching priority. Now, if you're familiar with Workload Manager and sampling, I do want to point out that work that is running on the CPU accumulates CPU using samples. Work that's waiting to be dispatched accumulates CPU delay samples. But work that would have run on a CPU but can't run on a CPU because of a cap slice is going to accumulate what we call cap samples. This particular slide just really talks about the concept of cap patterns or slicing patterns. So every service class period that is assigned to a resource group has a cap pattern assigned to it or a sleep pattern assigned to it. Now, this pattern is not static. It doesn't remain static throughout the day. It's reevaluated. In fact, it's reevaluated up to every 10 seconds. And the reevaluation of the slice pattern is really based on a number of different factors, such as the maximum itself, the weight to using ratio. So you can imagine if I have a maximum and I have a batch job that wants to run and that batch job is very CPU intensive versus another batch job which might be very IO intensive, the weight to using ratio of the CPU to using, waiting to use the CPU to actually using the CPU could be very different. Thus, the cap pattern could be affected. And also something what we call the absorption rates, which is when you do get to use the CPU, does this guy grab the CPU and just chug along all these CPU cycles? So a number of different factors are included in this, but eventually a sleep and a wake slice pattern is represented. So here I'm just happen to be showing 5 different groups, with a group at the very top, group 5, may have a very high maximum or may have just whatever, there's not a lot of demand in the group, so the sleep slice pattern is very sporadic. And as you get down to the bottom, you can see much more red, which means there's going to be much more of severe capping, much more severe sleeping. A couple of notes here before I go to the next slide is you can see that the sleep slice pattern, the sleep slices are actually distributed relatively evenly throughout the period. Because you want them distributed evenly because you don't want them all grouped together, because then you have the concept of slamming on a brake and nobody can run, and then all of a sudden you're off the brake and everybody can run. Instead, we want to use sort of the anti-lock brake mechanism where we want to slow down the work, thus the distribution of patterns. And finally, I just want to point out that typically when you have multiple resource groups for work, the slice patterns are such that when one guy is sleeping, another group might have an awake pattern. So that way, not everybody's sleeping at the same time, not everybody's awake at the same time. You want to distribute it because we want to have a slowdown effect. So real quickly, just let me show you 2 little examples. And here we're looking at a couple of graphs. These graphs have to be created by our product called Pivotor. But what this is trying to show is a chart that shows CPU capping samples. And John can make some comments about this, but in this particular environment that we're looking at, we see that we have some number of service classes called TM, ACM, 1, 2, 3, 4, and 5. And those are all service classes, and those all are each assigned a discretionary goal. Each one of those are in a separate resource group, so you can see the resource group name there of 1 RG to 5 RG. And in this particular example, each maximum represents a certain percentage of an LPAR. And what we're showing on this particular slide that is as the work is running, because the fact that we are accumulating CPU capping delay samples, that we actually do see that there is work actually being placed into these resource groups, and these workloads do actually want to use the CPU, but they can't because of the capping, because they're encountering sleep slices. And you can actually see that happening somewhat in the middle of the day there, and then point out, and John can elaborate on this more, that we actually see more capping for, let's say, group 5 on the left-hand side moving over to group 1 on the right-hand side. And John will relate to that a little bit as we go through to talk about why that actually occurs.
Yeah, Pete, what's interesting about this, you're kind of alluding to it, and we're going to get into it as we show you what we're doing under the covers, but this will correlate, you'll see in another slide, with the rolling 4-hour average increase. Because what we're doing under the covers with ThruPut Manager is gradually tightening things down, if you will, as your rolling 4-hour average increases. But yeah, we'll just give you a little hint for now. We'll get into the details a bit later on.
Okay, so we know capping is going on for this particular group. And the next slide, what this is showing is the average number of address spaces in just these service classes that are in these groups. So this is to actually show us that given these service classes, these ThruPut Manager resource group service classes here, that work is actually being placed into the group. And again, you can see group 5 oriented work here and moving over to group 1 oriented work. So on the previous slide, yes, we saw the capping delay happening in the middle of the day, but throughout the day, we actually see work coming in, and in this case, into the service classes that are in these resource groups for ThruPut Manager. And I just want to point out finally that what we're looking at in this particular slide is the corresponding MSU chart for this. So in this case, we see a maximum of 600 service units per MSUs, and then we have the red line, which is the actual MSUs consumed, and the blue line is the rolling 4-hour average. And during the same period of time, what we're trying to show here is that we know the work is getting capped. We know that work is actually being placed into these service classes, which have these resource groups assigned to them, that the blue line, the rolling 4-hour average, would actually be a much more severe peak had it not been for the fact that we were doing capping during this period of time. So the actual MSUs, yes, are going up, but they would have been up much higher had it not been for the capping that we saw on the previous slides. And with that, I'm going to change this control over to John, and I'll be available for Q&A. So if you have any questions about Resource Group or Workload Manager, save those for the Q&A session. And for now, John, here is the control to you.
All right. Got it. Thanks, Peter. Yeah, as Peter was kind of alluding to there, those were actual examples from a customer running ThruPut Manager automation. I'm going to get into it a little bit deeper into what we're actually doing. But as you saw in those last couple of slides, the idea is that we wanted to use resource groups in a different way than I think they were originally intended, rather than just statically slowing down work all the time. We want to be able to tie it to the rolling 4-hour average and dynamically use these at varying levels. We'll talk about how that works. So what we're talking about here in this slide, just some considerations. Static resource group maximums, first of all, they may conflict with WLM goals. As Peter pointed out, the maximum is going to be enforced regardless of what your goal may be. And it's on all the time. The quote that I have underneath there is actually taken right out of the WLM planning manual, where they actually, recommend that you don't use resource groups unless you have some kind of special need for that, because it's a static limit. It's on all the time. The point I'm making here as well in the second bullet, they're static. So you might limit a workload to a given service unit level, but you might actually have capacity available, both within your within the machine in terms of performance, but even from terms of budget. So it just doesn't make sense to have them on all the time. And then, of course, finding the right maximum, this is a moving target, right? Your demand and your utilization is going to change very quickly. So it would be very difficult to kind of manually do this. Just a quick level set of what ThruPut Manager is for those few of you that may not have heard ThruPut Manager. This is enterprise software. It manages and automates all your batch right through to the end of execution. It runs as a started task on each LPAR. It talks to JES2, it talks to WLM, it talks to Prism. So we have lots of information of what's going on in your system, so we can make the right decisions based on the policy that you have defined and based on the conditions, which, as I said, will change. Now, the primary benefits are automated service level management and automated capacity management. Just touching on these two key components, Service Level Manager, you'll see this term throughout ThruPut Manager dialogues, introduces a single queue in order of urgency. Because we're aware of the utilization levels, we're aware of the workload demand, we're aware of the business importance, we can order the workload queue regardless of how it was submitted or what class it was submitted in or what service class. You can override all of these things from your users to ensure that the most important workload runs first. Also very helpful to balance workload across systems and LPARs because we won't allow any one system to become overloaded while we're checking these utilization levels, for example, and overall maximize your throughput. But what I really want to focus on today is the automated capacity management function. The ACM is aware of your rolling 4-hour average, both local and across the CAC, the entire machine. We're aware of soft cap limits if they're present, or if you choose to not use soft caps, we're aware of your specified MSU target level. Yes, you can just give us a number, and we'll talk about how that works. And you can do that on an individual LPAR basis, or you can do that on a group basis, and you do not need to have caps in place for that to work. You can gradually constrain selected batch. One of our customers calls this a soft hammer approach, unlike what we'll talk about this later, hitting the wall, which is where if you have capacity limits in place and you hit those limits with a large amount of demand, that can be, well, shall we say, rather painful. I like to refer to the audible indicator of a problem. That's the phone on your desk. Will start informing you that things are not running well. It can reduce MSU consumption, reduce your overall rolling 4-hour average, and, of course, the resulting MLC invoice, which is the primary use for this function. But just to step back a little bit, and we touched earlier on the rolling 4-hour average, and there's an important point to make clear here. A lot of people are sometimes misled about when their peaks occur when we talk about what's driving the peak, for example, as well as which workloads contribute. So in the chart here, you can see the highest peak of almost 450 MSUs occurred at about 10 in the morning. Now, this is the highest utilization peak, but it's not the highest average peak. The rolling 4-hour average peak didn't actually occur until 12:30, like 2.5 hours later. And that's the peak that's the basis for your software charges. Most common method to limit the software charges is with soft caps, as we talk about, which is what the title is referring to. For those of you that aren't sure, DC is defined capacity, GC is group capacity. These are the two methods that IBM provides you to soft cap your workloads. But choosing to cap an LPAR or a group of LPARs is not always entirely without risk. This is what we refer to as hitting the wall, and is the primary reason that some shops choose not to cap at all. When the rolling 4-hour average exceeds the cap limit, your applications are immediately affected. Your phone will ring. When this occurs, your LPAR or your group of LPARs is going to be capped by Prism. Now, CPU resources are only provided to the LPAR at a rate that doesn't exceed the capacity limit. And this is regardless of the actual application demand. This effect is a lot like you're suddenly running on a smaller machine. And the capping is going to stay in place until the rolling 4-hour average is back below the capacity limit. In this example, it looks like it's about 3 hours. There's a misconception sometimes that the rolling 4-hour average cannot exceed a soft cap limit. It absolutely can, and as you can see in this example, it does. That's the red line goes over. It's just that when that is over the soft cap limit, your actual consumption or demand, as we may refer to it, will not be allowed to exceed that limit. You can see in the bottom right what we end up doing. You know, we panic, we analyze, we react, we adjust priorities, we try and kind of survive, but quite often we end up raising the cap. We might do that manually, or we might do that with some automated processes. And that will relieve the pain, if you will, for your applications, but it also establishes a new monthly MLC peak, because your software bill is based on either the peak rolling 4-hour average or the soft cap limit, whichever is lower. And that's the key point, whichever is lower. So in the top left example, the software bill is not based on the highest rolling 4-hour average that exceeded the cap. It'll be based on the actual cap level itself. However, to achieve that savings, you need to endure that pain. In the bottom example, where the customer has chosen to not endure the pain, they've increased their cap. But now the bill will be based on the peak rolling 4-hour average, which is not as high as the new cap level, but it is higher than the original cap level. So you have increased your bill by taking this action. Now, I want to launch a poll at this point, because this is actually exactly what we're talking about. If I can ask our moderator to get that going, what we might refer to as a capping event. Have you actually ever experienced this? Now, this includes, as you can see in the examples here, turning on engines. You know, we have to do that. We raise the cap, we hit the wall, or we just exceeded our subcapacity pricing limit. This is kind of, if you will, caving to the pressure. We certainly don't want to surrender the strength or reputation that the mainframe has for availability, so often this is what we have to do. We let that run. We can let that run for a little while. We'll keep going. So now I want to talk specifically about automated capacity management. And yeah, now we can see the results. So many of you have experienced all of these. Almost half of you have hit the wall, experienced that pain. Very common. A good number have raised caps. A good number have turned on engines, exceeded subcapacity pricing limits. Only some have not experienced any of these at all. So certainly understandable type of problem that we'd all like to avoid. I think this is where automated capacity management can help. You can lower your rolling 4-hour average, and this is the method. First, you can choose what workloads would you like to constrain. If you're using basic soft capping, defined capacity, group capacity, you're capping an entire LPAR. That means the scope of the workload that will be limited is potentially all of the workload on an entire LPAR. Now, if you've got an entire LPAR that runs nothing but test, sure, that works. Most of us don't do that. We mix our workloads. There can be some important, some critical, some less important, some kind of medium workload running. It really would be nice to be a lot more granular, and with ACM you can be. Next, you get to constrain when. So you're not just capping all the time as you would be with a static resource group or with a soft cap limit. And this is based on your policy, and this is based on a rolling 4-hour average target. So that can be an actual soft cap limit, should you choose to use one, or an actual MSU value. How to constrain? You can either hold the selection, so work that would have normally started, you can actually prevent it from starting based on the policy. Or automated resource groups, which is what we're focused on today. You will have multiple resource groups at the disposal of ThruPut Manager. We'll talk about how that works in order to gradually limit specified workloads, workloads specified only by you and only when you decide they should be constrained. And finally, to that point, how strictly? Do you want to constrain concurrency? That is the number of concurrent jobs. Normally I run an unlimited number or a very large number of different classes. I can limit the number of each category of job. Or the resource group capacity, like Peter talked about. You can put these into a service class that is within a resource group with a maximum. You set that maximum level. And there's not just one. multiple resource groups. So depending on the conditions, you can set up a policy that will automatically move the workloads in and out of these service classes within these resource groups that will vary the level of constraint to your designated workloads. Now, the result of that, of course, is that, firstly, your rolling 4-hour average comes down. Secondly, your critical workloads will run much better because by constraining less important work, you're providing more resources for the more important workloads to run well, even though you're working within, a budget-constrained environment, if I can call it that. Now, this is done automatically. Of course, you don't want, the hitting the wall scenario where you're kind of scrambling and trying to figure out what to do in order to provide more resources after you've hit this wall. Most of us that run mainframes know that transactions run in the thousands per second. Jobs, we're running thousands of those, tens of thousands of those per day. We can't really afford to be manually reacting. We want to set up our policy, design what we want to do, and let that policy work. And finally, again, just to be clear, you can do this with or without soft caps. So how do we do it? Screenshot here just from setting up a resource group within Workload Manager. So not reinventing the wheel here. Go into your Workload Manager policy, set up 5 service classes and 5 resource groups, each with varying maximums. The number is up to you, but most shops will choose typically 5. You don't have to classify any workload into the service classes as you normally would. ThruPut Manager will take care of that. So you just set up your resource groups. Then within ThruPut Manager, you set up what we call capacity levels. Now, capacity levels are shown at the bottom of the screen here. You see levels 1, 2, 3, 4, 5 set to 99.9, 95, 90, 85, 80. What those represent are the percentages of each resource group, the percentages of the limit that you have defined. So if you have a soft cap level, for example, at 1,000 MSUs, capacity level 3 is 90% of that, or 900 MSUs. That's all that means. Again, you don't have to have a soft cap. You may simply define an MSU number. You define an MSU number of, say, 500 MSUs, 90% of that, 450. So that simply tells ThruPut Manager when the rolling 4-hour average reaches this threshold, I would like you to take action, and you define specifically what that action is. Finally, you classify your workloads. Again, you likely don't want to defer everything. If you were going to defer everything, you might just cap the whole LPAR. We don't want to do that. We want to be very selective. We have critical work. Even with batch, we very likely have critical batch. So we simply don't want to be constrained. It's got SLAs. Those SLAs need to be met. But you can specify non-critical batch workloads and designate them as eligible for constraint at each capacity level. So you may have a test workload that is eligible to be constrained at, say, 80% of your limit. So before I reach my chosen limit, I want to start slowing things down. Now, why do you do that? Why do you do that is because the rolling 4-hour average does not move quickly. It's like a big tanker. It's like the Titanic trying to turn at the last second. It won't work. Can't wait until you see the iceberg. You can certainly adjust your instantaneous workload, but the rolling 4-hour average is precisely what the name suggests. It's the average over the previous 4 hours. In order to bring down that number, you need to act proactively. If you don't want to exceed 1,000 MSUs, you can't wait until the rolling 4-hour average gets to 1,000 to take action. You need to take action earlier, and that's why we've implemented this method. So at each capacity level, you designate which workloads would be eligible, which workloads would be not, and their level of constraint. Here's just an example of what it looks like. So say capacity level 5, I've set a percentage of 80%. Now, all these are customizable, by the way. You don't have to say 80%. Maybe you've got a really big machine, and 20% left over is still a lot of capacity. You might say, I don't want to start doing anything until I get to 90. You can absolutely change these numbers. But in this example, I started 80%. So my rolling 4-hour average trigger is at 800 MSUs. What do I decide? I've decided that I'm going to move my lowest test batch into a resource group with a 15% maximum. 15% of the L power is the most that the work that gets moved in there can achieve. So that should have some effect in terms of slowing things down. If the rolling 4-hour average continues to rise, if I get to 85, if I get to 850, if I get to 900, I continue to move additional work. Now you can see what we're doing here. Again, you can customize this, but what we're doing here is you can move more work into the resource group, which will slow things down further, or you can decrease the size of the resource group, the percentage from 15% to 10 to 5 to 3. Again, you can choose those numbers. Because if you think about a resource group, it's like a box. You're putting your workload into a box. Now, by deciding the percentage, what that is deciding how big do I want this box to be. Smaller percentage makes for a smaller box. As well, by deciding to move more work in, you're making the box more crowded. So you can see when I move from capacity level 4 to 3, from 850 to 900 in my rolling 4-hour average, I didn't change the size of the box. They're both at 10%. But what I did at capacity level 3 is I said, in addition to the test batch, I want you to move some development batch into the box as well. The size of the box is the same, but I've made the box more crowded, which means it's much more likely to hit its maximum, which means it's much more likely to incur cap slices, as Peter described, which is going to pull down your rolling 4-hour average. As I mentioned, all of this is customizable, these numbers. I want to just talk about the effect of it here, because this is also from an actual customer. You think about phase 1. This is the proactive phase. This is capacity levels 5 through 2, where my rolling 4-hour average, which is the red line, as it's approaching my chosen limit, I start moving designated workload into the capacity service classes, which are in the resource groups. What you can see, the blue lines, which represent the demand on an interval basis, those start coming down. This starts flattening out the rolling 4-hour average as I approach my limit. Otherwise, it'd be very sharp, and we hit the wall. We don't want to do that. Phase 2, if I do actually reach my limit, now I'm at capacity level 1. Now I'm constraining the maximum amount of work that you designate to the maximum degree that you designate in order to really hold the line on your consumption. This is going to keep your rolling 4-hour average down as much as possible while allowing your critical work to run. In phase 3, we see that things are starting to get better. The rolling 4-hour average is dropping. Something I should have mentioned earlier. ThruPut Manager, I mentioned that it's aware of these things from talking to WLM and Prism. It's actually checking all of these key metrics every 10 seconds, the same time frame as a WLM policy adjustment cycle. You need to do this because the rolling 4-hour average is changing, the demand is changing, the utilization is changing. Heck, the cap may change. You might move it. We need to be aware of that. So we're automatically checking these things and making these constant adjustments about where to move your work in order to get the critical work through while maintaining your budget goals. This is another customer chart on the top left, and just pointing out that we can work with defined capacity, group capacity limits. If you choose to use these soft caps, if you're using them today, with ThruPut Manager, you can lower those caps. The example that Peter was showing at the beginner is from an actual customer, and I can tell you, without naming the customer, that since we've actually even analyzed that data that you were looking at, they've already decided to lower that cap further because ThruPut Manager is deferring non-critical work for them, lowering the rolling 4-hour average, allowing them to bring down those MLC charges. Very, very happy customer. Similar effect here. You can see in the chart in the top left, the red is the interval demand, the blue is the rolling 4-hour average. You see how it's initially on a very sharp slope. I mean, this is a workload that's heading for the wall, the green line being the wall. As it gets closer, though, ACM kicks in, starts gradually slowing down the non-critical workload, and you can see the rolling 4-hour average gradually starts to flatten out. Skims the line without hitting the wall. You're still getting the most value out of your hardware. You're protecting your critical workloads. You're holding the line on your budgets, and they get through it. This more, I guess, innovative, if you will, customer that absolutely doesn't want anything to do with caps. They simply want to reduce their bill. The same algorithms run within ACM. So by simply specifying a target, in this case, they were hitting 300 MSUs in the rolling 4-hour average. That's in the top left chart. And they set a target of 265. They didn't want to achieve that, or they didn't want to exceed that, excuse me. So they simply plug that number to ThruPut Manager, ACM, and say, do it, without a cap. And what you see in the bottom right chart is the result. The pink line is the new rolling 4-hour average. Again, critical workloads are still getting done. Because there is no cap, too, you know, the nice part about this particular approach and really, you know, talking about the title of the webinar, Reduce MLC Without Capping, is because there's no cap, there's no risk to your critical applications. There is no wall to hit. Should you have some critical online application that has a huge demand all of a sudden, it'll get it. We're not going to get in the way of that. These are some of the results that you can see. Actual government client from last year. The chart is just showing the two machines with the relative reduction in MSUs on each machine and what that meant to their monthly MLC charges. This is strictly IBM software charges. This isn't even accounting for anything else. Really substantial savings. So, summary. Resource groups are absolutely a powerful tool, but I would suggest that they are just limited by their static design. Now, ThruPut Manager automation gives resource groups new life as a dynamic cost-saving instrument, and this is with or without caps. We've got a lot of customers that are very happy with it. We'd be very interested in what you think. Send us your data. Our MSU analyzer can provide your potential MSU reduction, get an estimate of where you might land. Peter's Pivotor can provide all kinds of detailed insight into your performance. So please contact us about that. I'm going to go into poll number 2 at this point, and then we're going to head into the Q&A, if I can ask. There we are. Just so for those of you that may not be aware, CMP stands for Country Multiplex Pricing. There's been a lot of talk about this offering from IBM, and it seems like a great idea on the surface, absolutely. But we agree with Cheryl Watson's advice that it's critical to lower your baseline as much as possible before you convert. This will definitely help you in the long run, but you really need to know what you're doing before you go to CMP. So wait for the results of that poll to come back up. We can certainly talk about the results of that and anything else that you've seen today. I'm available. Peter is available. Also, I'd like to point out joining us Selby Shanley and Scott Chapman. Selby is the principal developer of ThruPut Manager's automation code, and Scott's the lead developer of Pivotor. So feel free to throw these guys some good curveball questions. At this point, I think I'm going to turn it back over to IBM, and we will be happy to take your questions. Thank you.
Thanks, John. Okay, we have some great questions come in. Would you say capping will become simpler with country multiplex pricing?
Would capping become simpler in country multiplex pricing? Selby, what do you think? Oh, Selby's muted.
There I am. I'm unmuted.
There you are.
Not necessarily, because as was pointed out by Cheryl Watson, you still have to establish your base. So you still have to watch out for what is it you're using and what is your peak rolling 4-hour average.
Yeah, I would agree with that. I was reading up a little bit on the announcement. It's going to be GA the beginning of October, and when you read the details of what they're asking for in this baseline, they're looking at your 3 months of consumption, specifically looking at MSU consumption. So I'm not sure that you would necessarily be saved by capping.
John, can you constrain by time of day plus R4HA?
Oh, wow, there's an interesting idea. Well, you can certainly have multiple policies, but you know what? I'm going to throw that over to Selby as well.
Yeah, the way that you would handle that is you would enable different policies, which you just activate on the fly, and you could set different limits if you want. Some people have also done automated pieces to actually go and change their defined capacity or LPAR group limits. And ThruPut Manager will see these changes and just start managing to the new limit.
Okay, a couple of related ones. Back on slide 10, someone was asking, what does RG max stand for? And then a question came in later, can RG be turned on and off using a shift policy?
RG max is resource group max. Oh, go ahead, Pete.
No, resource group maximum. That's all that stands for. Is the maximum for a resource group, which could either be service units per second, percent of an LPAR, or in terms of CP worth of capacity. And in terms of it being able to be turned on and turned off on a policy shift, yes. If you change the policy, you can set one policy to say, I want the maximum to be one number, or another policy could have a maximum to be another number, or maybe no max at all. But you can definitely change that through different policies, and that could be changed during a shift.
Okay. Kind of comment question. This is efficient on one LPAR. Can it be used to do the same thing across LPARs? I don't think, but I'm asking anyway.
Oh, I'm going to say absolutely. Selby's going to get excited because I don't know how much you want to reveal, but the answer is yes. We do have the ability within ThruPut Manager. We haven't a name for it. You may have heard within the capping genre of group capacity, or sometimes referred to as LPAR groups. We have something called LPAR sets. Selby, do you want to talk about that?
Yeah, I can talk about that for just briefly. First of all, let's just talk about LPAR groups because we will manage to an LPAR group of the existing IBM LPAR groups. So you could have an LPAR that's running a ton of test load that could be deferred, but it's in a group that is at its limit. And we will start pushing the load down on that LPAR, allowing the other LPARs to get more of the LPAR group limit. And thereby, they're not as affected as much, and you can keep the LPAR group limit down further. We also have a new concept called LPAR sets, which is subsets of the LPARs on a CPC that you define to ThruPut Manager. And then you assign them a limit, and ThruPut Manager then will manage to that. And it will make a choice. An LPAR can have its own defined capacity. It can belong to an LPAR group, and it can be a member of one or more LPAR sets. So there's all these different limits that can be assigned, and automated capacity management sorts it all out, worries about the limit that is the one that you're closest to, and then manages the load on that LPAR so that across a set of LPARs, we manage to a limit for that subset. And one of the obvious uses is you might subset the LPARs based on what software is licensed and running on each one of them.
Does ThruPut Manager manage other workloads besides batch, like CICS, DB2, DBF, etc.?
Not today. Selby?
No, it does not. No, it does not.
Can you go into some detail about how you are changing service classes while work is running?
I guess that's fine. I guess how we're changing them. That was the question, right?
Yeah. How are you changing service classes?
We know to which service group or subset of your batch workload it belongs, and therefore whether or not, based on the current capacity level, that workload should be assigned to a given service class. As jobs are selected, they're assigned a service class that's appropriate for that time and the characteristics of that subset or service group, that subset of the batch workload. If the capacity level changes, then ThruPut Manager, the automated capacity management part, will go and change the service classes for those using a standard API. And they will get switched over into the new service class, and it will remember that. And as the capacities levels change, the service classes will get switched as appropriate. Part of the good thing about this technique, it means that there's only one extra active service class period in your system, which minimizes the overhead in WLM. And after you are nowhere near your limits, it will simply switch all that workload back to their normal service classes.
How does ThruPut Manager work with existing capacity management products like auto soft capping?
Selby, I think you're on a roll, man.
In this case, it depends on what the product is doing. But if the product is changing a particular limit all the time, it's more difficult to manage to that limit. It's sort of a moving target. So what we allow instead is you provide the limit or limits to ThruPut Manager, and it manages to them. And we tell it to actually don't pay any attention to this other limit because it's bouncing up and down all over the place. And that includes LPAR groups. So you can define limits per individual LPAR, and you can also provide limits for different sets of LPARs, including the whole CPC, all the ZOS LPARs on one machine, or different subsets which can intersect, which is something that LPAR groups cannot do. And that's how you would coexist with a third-party capping product.
Okay, I've got one here I hope you're familiar with. We resource limit our AB, Initio, OMVS processes that run on the mainframe. These processes consume excessive CPU. How does TM manage OMVS workloads?
So OMVS stands for Open Edition, renamed to Unix System Services. So not being batch workloads, we would not directly manage those particular workloads.
Okay. So does the LPAR set actually enable a hard cap on the LPAR with respect to batch only?
Okay, I guess this is really mine. In terms of LPAR sets, LPARs, when you establish a limit within ThruPut Manager, it's a limit that ThruPut Manager manages to. WLM is not aware of this limit. And there is no capping involved, which allows you to implement this without actually having soft capping if that's what you wish.
Okay. Try this one. Billings happen on a machine level, but capping will happen at the LPAR level. If there's a spike in some other LPAR, will it affect the R4HA?
Well, the answer is yes. I don't know if I should send this one to Selby or Peter, actually. Peter, you want to take a crack?
No, the answer is give it to Selby because he knows probably more about it from the ThruPut Manager point of view.
Okay.
Okay, just in terms of when you're managing to this, when an LPAR goes up, it affects what is happening concurrently over the whole CPC. It's a bit of a complicated answer because it's how the SCRT processes the data. It actually does it on a product-by-product basis, for example, IMS or DB2. And it looks at the maximum rolling 4-hour average for the month across the subset of the LPARs that are running that particular product. So if it's DB2 and you got it running on 3 out of your 5 LPARs, then for the DB2 bill, it will be looking at the maximum rolling 4-hour average for the month across those 3 LPARs. So that when the LPAR goes up, yes, it can affect your bill. It depends on what's going on the other 2 and whether that creates a new peak for the month.
So, gentlemen, with the time we have left, I think this is a good question. And just for those of you, if you did ask a question and we did not get to it in the time we had today, someone will reach out to you via email. The last question, do you have a tool I can run that will show the MSUs I can save?
Absolutely. Yes, we call it the MSU Analyzer. Send us your data. As I said before, if you send us your SMF data, RMF data, type 7072s primarily, although there's lots of other good information there that Peter could tell you with Pivotor. But specifically to the question, yes, what we would do is analyze a month's worth of data, identify the top 50 rolling 4-hour average peaks, identify the batch contribution to those peaks in terms of rolling 4-hour average numbers, not just utilization numbers, and absolutely you can estimate what your potential MLC reduction would be in MSUs, and you can convert that to dollars, or you can redistribute that work to other applications.
That's all we have time for today, unfortunately. Very interesting. I want to thank everyone for attending today's webinar, and I especially want to thank John and Peter for sharing their expertise. Later this week, we will be sending out a link to a recording of today's presentation as well as to the charts for everybody who registered. And basically, that concludes our webinar. Thanks again, and have a great day.
Thank you, everybody.